Proof by cases is a variation on direct proof where we start by doing a direct proof, but then at some point we need to consider two different possibilities and we do them one by one. We look at, okay, here's a possibility, we'll prove something about it, then we'll consider another possibility, we'll prove something about it until we've exhausted all the possibilities. And if at the end of each of those possibilities we've proven the right thing, then we have completed the argument. So here's an example of a theorem we can prove using proof by cases. Theorem, for any integer n, the integer n squared is even if and only if n itself is even. So this doesn't necessarily look like something that requires us to make decisions, but let's look at the structure a little more carefully. If we write this out in logic, what we're saying is that for all n in the set Z, E of n, so here I'm using E to mean the predicate that n is even, implies E of n squared is also even. And remember, if and only if, that means I'm looking at a biconditional or an implication that goes both ways. That means I also need to look at E of n squared implies E of n. Okay, so this still doesn't really look like a case of cases, but let's look at the contrapositive of this second term here inside the and. It's enough to prove the contrapositive, since the contrapositive is equivalent to the original expression. The contrapositive is E of n, not E of n, implies not E of n squared. And not E, so n is not even, that's the same thing as saying that n is odd. So now I have something that looks more like a situation where I need to think about cases. I'm going to have a case 1 corresponding to n is even, and a case 2 corresponding to n being odd. So with those two cases in mind, let's see if we can prove the statement. So proof, move that up just a little bit, proof. Okay, so proof, what I'm going to do is I'm going to go case by case. So case 1, n is even. So now I'm rolling direct proof. If n is even, then n squared is even. So I'm going to say then, since n is even, n equals 2 times j for some integer j. Then we can do some algebra. N squared equals 2 times j squared, which is equal to 4 times j squared. I'm going to choose a new variable, k equals 2j squared. Then we have n squared is equal to 2 times k. So, since k is an integer as well, if I take an integer and square it and multiply it by 2, I still get an integer. Since this is true, we have that n squared also satisfies the definition of an even number and is also even. So that was case 1. I'm not done yet. I still need to do case 2 in order to complete my proof of this claim, case 2. Okay, so for case 2, I'm considering n is odd. So in this case, by definition, then n equals 2j plus 1 for some integer j. Then we're going to do a pretty similar calculation here. It's just going to be a little bit more complex. So this time, n squared is equal to 2 times j plus 1 squared. Got a FOIL. I'm going to get 4j squared plus 4j plus 1, which it's going to be convenient for me to write this as 2 times 2j squared plus 2j plus 1 on the outside. Choosing k to be equal to 2j squared plus 2j, we have that n squared is equal to 2k plus 1 for some k in the set of integers. Therefore, we've shown that n squared is odd. And that completes our proof. So what we've done in order to prove this theorem is to essentially turn one proof of a larger claim into two proofs of smaller claims. We break it out case by case. And then once we've exhausted all the possible cases, we have completed a proof by cases. Let's now discuss one of the simplest and most convenient kinds of proof, and this is particularly a method of disproof. You use it to show that some kind of statement about everything in a set is not true. Not true. So disproof by counterexample, we use it if we have a statement that we're looking at and we're going to show that it's not true because there's some possible pieces we could look at that make the statement false. So here's an example. Here's a statement. Here's a statement for any three integers, x, y, and z. If x times z is greater than y times z, then x is greater than y. This is a statement. It's a statement about all possible groups of three integers. If I check an inequality, x times z greater than y times z, I can cancel the z and get a new inequality, x is greater than y. So another way we can look at this is saying, okay, this is a statement about for all x, y, and z in the set of integers, some predicate about these implies some other predicate. So it has the same structure as this idea. However, theorem, this statement is false. This is not a correct mathematical statement about the integers. How do we know? How do we prove the theorem that this statement is false? Proof. Let's start. Here's my proof. I'm going to prove by counterexample. So if you prove by counterexample, you start by saying, here's a counterexample. So what I'm looking for in a counterexample is a setting, a choice of x, y, and z that makes the first part true, but the second part false. So I'm going to show the antecedent is true, but the consequent is false. Okay, so what are we going to do? We are going to choose, and I can choose anything I want to. I can choose x equals 1, y equals 3, and z equals -1. How did I know to choose that? Experience and some guessing. And this is a place where it's okay to guess until you find something that works as a counterexample. So in order to complete my proof, I need to check that the first inequality is true. Let's check that. X times z, well, that's equal to 1 times -1. That's -1. -1 is larger than -3, which is the result of doing y times z. But, so now I check that this part is true. I also need to check that this part is false. So let me check that as well. Is it the case that x1 is greater than 3? Obviously not. In fact, 1 is less than 3. So x is less than y. Now I am done. I have given a counterexample. I've shown that there are some possible choices for x, y, and z that make this purported statement false, and so I've proven my theorem that this statement is not true. It's really important to remember something. Really important to remember something. Examples and counterexamples are never enough to prove a claim about all possible things in a set. So if I have a claim of the form for all x in S, P of x implies Q of x, I am never ever going to be able to prove that that is true using an example or a counterexample. The only thing I can use examples and counterexamples for are to disprove those kinds of claims when it's false, like I did here. So when you are thinking about a proof, you might want to give an example that makes the proof or makes the theorem true. That can feel tempting. But what we always need is a sequence of steps to prove a statement. I can only use counterexamples to disprove a statement. So if you find yourself trying to prove a theorem using an example or a counterexample, you're probably not on the right track. Save that for disproving statements using counterexamples, and save steps like direct proof and proof by cases and other techniques which we'll learn soon in order to prove theorems.